Okay, and so I've had some feedback about this title, that it's a little bit ambiguous. It was his master's topic, so that's the first hint that maybe I should do that. So I think I need to redefine the topic here a little bit. What I mean is multiple kinds of behavior being observed in order to recommend multiple kinds of things. So that's what I mean by multimodal. I also call this polyvalent recommendations, but that's even worse than multimodal. Nobody understands that. So what we're going to talk about today is, what is this multimodal stuff? I'm going to define a very simple recommendation architecture, which actually I recommend, that I think is very good for simple recommenders with one kind of behavior and one kind of recommendation. But it extends very simply and very effectively to multiple kinds of behavior as input and multiple kinds of recommendation as output. It also allows Boolean narrowing of the recommendation set. It allows geographical constraints and things like that. And it has a very robust deployment architecture. So we'll talk a little bit about that architecture. I'm going to give you some scary math. Probably not so scary here, but some people are excited by Greek letters. And then I want to talk about how we put all this multimodal stuff into a production environment. And then some final thoughts. Just some logistics. I'll repeat this at the end. You can get to me all kinds of ways. Tweet to various addresses. Send me email. You can find my private email on the internet everywhere. Or you can even subscribe to the Mahood mailing list where this is all happening. We're about to produce a 0.8 release of Mahood. Been a lot of activity this week, a lot of bug fixing, squashing these bugs. A very impressive Jira graph of how many bugs were fixed versus reported. You'll be able to get my slides from the Buzzwords website or sometime late tonight. Late tonight might mean tomorrow on SlideShare. And there's some suggested hashtags, of course, including the Buzzwords hashtag. So recommendations is often called collaborative filtering, but I think that it's better to just call it a social algorithm, because collaborative filtering has this presumption of particular kinds of input. Often it assumes that the input is ratings and assumes that the desired output is to estimate ratings and things like that. And I find that a very limiting and, practically speaking, an inaccurate characterization of what we really want to do with recommendations. So let's call it just recommendations. The basic input for the simplest kind of recommendations is a case where some people or users or machines or something, actors, interact with items. It's a dyadic structure. It's a very simple sort of thing. And we want to suggest interactions that have not yet been observed. We want to say, here's things that this actor would like to do, but otherwise might not be able to find. So this is a very simple framework. And inherently, because we have very, very many items and very many actors, there are too many items for every interactor to interact with. And so the data that we observe, the data we have to work with, is very sparse. And that's what causes most of the difficulties in this field. There's many examples that people have seen. People buying books was one of the first public ones. That was Amazon, of course. Web visitors rating music. That was some of the first research things coming out of MIT Media Lab. I've been able to construct a couple large systems like the Music Match recommendation system, which involved people listening to music. But there was the beginning of implicit behavior. Implicit behavior of one kind where people skipped the music or not, which was not necessarily the same as selection activity, but it was an implicit behavioral observation. And we also built a very large video recommender, AdVio. But what I want to talk about today is not so much just ordinary recommendations, but it's this multimodal things. And the idea is that we have lots of different kinds of behavior, especially as we move into using recommendations with large companies. They see people act in many ways. They see them tweet. They see them use a credit card, perhaps. They see them act on the web. They see them request coupons or eventually act on the recommendation. So they have many kinds of behavior, and this question comes up over and over again. How do I merge these different kinds of behavior? Even if it's very simple. If I rate a movie and then watch it, what do those mean? Is a rating of 5 the same value as watching a movie? What about rating it 3? Is that a negative thing or a positive thing? Well, how do we combine these behaviors into coherent recommendations? And that's the key crux of today's problem. And having a complete picture that is integrated across all of these different kinds of behaviors is exactly the goal of what we want to build. And there's many, many kinds of behavior, even on a very simple website. And so let's look first at how we build a normal recommendation system. Oh, we actually have a balcony. This is so exciting. It's just like a rock club, isn't it? Look at the speakers and things. Woof. I'm not going to jump into the crowd, though. So the basic idea of recommendations is we look at history and we try to say, what are the things people would have done if they just had a chance? And so with ordinary recommendations, we have users and we have items, and they interact in some single way, or we compress everything into a single way. So we have that history. And the history usually looks kind of like a table or a log file. And it has codes for users. That's the user ID on the left. And it has codes for things. This is the raw data. And if we look here, we see that user 1, for instance, has interacted first with thing number 3, and then toward the bottom with thing number 1. Now, this is an inconvenient way to look at this, so we very often do what's called sessionization. We rearrange the data so that every user's history is next to that user's history. So now it's much easier to see that user 1 interacted with T1 and T3, thing 1, thing 3. We've lost the element of time here, but the ordering is not so important. The whole idea of cause and effect in recommenders is often backwards anyway. So we don't much care about the time aspect. But we see that T1 and T3 were watched or interacted with by user 1, also by user 2. And so we see 2 co-occurrences of T1 and T3 in these data. T1 and T4 co-occurred once, T2 and T4 once, and T3 and T4 co-occurred in user 2's history. This idea of co-occurrence is what we're after in many ways. The co-occurrence is the indicator that there's something connecting two items. Now, we can draw this either as a matrix like this or as this long log file, but we can draw it very economically as this is a matrix. And if we were to use it as a matrix, then multiplying on the right by a vector of things would give us a vector of users. So this matrix translates things to users. And if we transpose the matrix, it translates users to things. Here's mathematically a very concise way to do that. We can talk about multiplying by a history vector there times our history matrix. This history vector is for one user, the user who's of interest right now, and A is the history matrix of all users. And so AH gives us users who do things in common with the items in H. That's easy. And then if we want to translate back to items, this equation says users who do this also do these other things, interact with these other items. So that's, in a very tiny little notation, a traditional way that people describe recommendation engines. And we can move the parentheses because it's simple mathematics. And so offline, we can compute this A transpose A. And in fact, A transpose A is the co-occurrence matrix itself. If we multiply that out, we get a thing by thing matrix. We've now averaged over all the users who exist, and this thing by thing matrix implicitly, without having to do it explicitly, goes from things to users and back to things. But it encapsulates it. It allows us to do most of the computation offline, so it directly converts from things to things. Now, there's a problem with raw co-occurrence as we see it there. The shape of the computation is right, but the details are wrong. The details are wrong because there are things like the welcoming message at VO. The CEO would say, hello, thank you for coming, and everybody had to watch this video, which meant that it co-occurred with everything. And so raw co-occurrence would cause that video to be recommended to everybody again and again. It was horrible. And so what we want to find here is not just co-occurrence, we want to find the idea of anomalous co-occurrence. The co-occurrence that is extraordinary. We see the general patterns. Everybody watches this. Everybody steps into an elevator at some time in their life and hears Beatles music. These are uninteresting occurrences. Therefore, the co-occurrences with those uninteresting events is also uninteresting. And so we need to find just the anomalous things. And the way we do that, let's look at T1 and T3. They co-occurred twice. But we can look at that in more detail. We can take just that one T1, T3 co-occurrence, and we can say, how interesting is that? So we look at how often T1 and T3 co-occurred, but also how often T1 occurred with something that is not T3. And conversely, how often did T3 co-occur with something that is not T1? And then how often did not T1 occur with not T3? And that gives us a little 2x2 matrix. And if we look at a bunch of these matrices, in the upper left is an example where A occurs about 1% of the time overall, regardless of A or B or not B occurring. You can see it's about 1% of the time. And B also occurs, B is horizontal rows, B also occurs about 1% of the time. Now, if we look at only the cases of A, we see that B occurs about 1% of the time that A occurs, 1.3% of the time. This is just not very different. It's about the same as the occurrence in general. So we would say that's not very interesting. We have lots of data, and it's just a boring co-occurrence. If we move to the upper right, then we have A and B occurred once and only ever together, 100% of the time. Well, this is not very interesting either because we only have 3 data points. So anything could have happened. I mean, if you have 1 data point, anything that did co-occur had to co-occur. And at 3, it's just not very exciting. It is a little bit more exciting than something that we have enough data to say it is truly boring. The one in the upper right, we just can't say, is it exciting or boring or not? We don't know yet. In the lower left is a similar case where A and B occurred together, but they are relatively rare. So we have at least a coincidence, at least the beginning of anomaly. It's a little bit more interesting, but not very. I mean, among the millions of things that co-occur, that probably isn't going to make the list, but it is more interesting than the upper right. And then down in the lower right, we have a case where A and B co-occur 10 times out of 10,000, or 100,000 roughly, samples. Now that begins to be very interesting because they never occur separately, they always occur together, and so we have something that we can score. And there's a way to put a mathematical score on these that gives us this very, very nice intuitive ordering. It matches our intuitions very nicely. And happily, it's a very, very simple formula for this sort of thing. And it's a surprising thing. It was developed many years ago, but it has a nice robustness to these cases of coincidence, like the 1 out of 3 coincidence sort of things. It doesn't overrepresent those 100% but boring cases. And it's been tested thousands of times now, and in general, it's one of the top few methods in most of these tests in a variety of different things, in finding structure in language, in identifying language, in finding structure in genomes. It's been tested in all of these many, many different applications, and it happens to be very robust and gives us nice intuitive things. And so it's called log likelihood ratio. It's a generalized log likelihood ratio, and the square root of that is usually what we want. And so the idea is that it is mutual information. That's the entropy of the matrix minus the entropy of the row sums and the column sums. And if we take the square root of that, we have a very nice scale that is very similar to standard deviations. You can find the exact code. There's more lines of code than this because it has test cases. But that bit.ly link has exactly the code in R to do this. Mahout also has this. So this is the crux of how to do this co-occurrence to recommendations. And the idea is that we take whatever is significant in these co-occurrences and we reduce it to a binary case. We only retain ones and zeros. Ones where we observe anomalous co-occurrence, zeros everywhere else, and we don't even store the zeros. Okay, so this is so far so good. We can build recommendation systems like this. Each row of that reduced co-occurrence matrix, the ones are what we call the indicators for that row, and we can use those indicators whenever they appear in the single user's history to build up a score of which things we indicate, which ones we recommend. It's very simple to deploy. You can actually do this in a search engine. The elements, the non-zero elements in that row can become tokens in a field in Solr or any search engine of choice, and you can build a recommendation engine because the native weighting of the search engine works very well to weight these ones and zeros. And the search engine itself is implementing the sparse matrix multiply that we had earlier, the A transpose A times the history. So that's a really nice way to build a recommendation engine, and it's built into Mahout. It has some very, very nice characteristics. It has a long history. Lots of people use it. Dozens and dozens of companies use it. There's good case studies of it. Overstock.com recently had yet another case. There are commercial offerings that use very similar things like Mirix. Mahout Committer started that company. You can do a lot of this. It's a proven track record. It very often is very difficult to beat, even with very elaborate mathematical models. And it's very well socialized, meaning you can go ask somebody about it and get good answers. So that's all wonderful. Sounds like that's the end of the talk. But it's only 17 minutes in, so we have to talk about something else too. Let's talk about what's wrong with it. And the big, big problem here is people do more than one kind of thing. And that more than one kind of thing has more than one kind of meaning, more than one kind of implication, more than one kind of strength of the recommendations. And so we have this problem there. How do we combine these different kinds of behaviors? And the basic idea is that we don't do co-occurrence anymore, we do cross-occurrence. When one kind of behavior co-occurred with another kind of behavior. So we cross from one set to another. And we get cross-recommendation. The usual response that I get when I say, let's do cross-occurrence, let's do cross-recommendation, is very succinct. People say, eh? Because there is no socialization around this kind of solution yet. So if we take the original formula, A transpose A times H, this is dyadic learning from users and things. We have a dyadic set. But why not have triadic? Why not have users and type 1 things, type 2 things? Why not p-adic things? And in particular, why not cross-learning? And the way we do cross-learning is we replace one of the A's with a B, a different kind of history mechanism. That A represents interactions with things of type 1 and B with type 2. Now, I have to admit that the first time I was talking and I said, gee, by symmetry we could do this, and it would, of course, be uninteresting. And one of the people in the audience said, why? I go, well, it's obvious, because that's the way I pronounce I don't know. A lot of people do that pronunciation. And he goes, why is it obvious? I go, try it. You'll see. He tried it, and it worked really well. So I've changed my talk a little bit. It's no longer obvious. And in fact, I think it's a very clever idea. I'm glad I wrote that down. I just can't take credit for it because I said it was stupid. And so let's take an example here. Users enter queries in the A matrix. And then the things will be the words that they type into the queries. And the B matrix will be videos that they view. So we have users and we have videos. two different kinds of behavior, two different kinds of things. And A transpose A will give us query recommendations. Did you mean to ask for such and so? You type in a query, and it gives you back alternative query words. That's nice. B transpose A will give us video recommendation. You might like these videos too, or at the bottom of the video page, you can put those down. But B transpose A is a different beast. It takes in search terms and gives you back videos, but it does it without metadata. It never indexed any of the text associated with the videos, which usually is garbage anyway, so we don't need to index it because it doesn't help. But this really does produce a very nice thing that acts like a search engine. And it's a wonderful thing. First, we're abusing the search engine to create a recommendation engine. And then we're abusing the recommendation engine to recreate a search engine. It's a wonderful tail-swallowing exercise. Here's an example. I'm not going to talk too much about this because I want to go to the next generation beyond this. We built one of these at VO, and we put in a query into 1 million videos that we knew had no videos by Paco de Lucia, at least that we could find. Paco de Lucia is a guitarist, a Spanish or Italian, I'm not sure, I think Spanish guitarist. And the conventional metadata search brings back Hombres de Paco, because it matches. See, Paco, well, it must be the same. That's what the metadata says. The recommendation search brings back much better results. Here's the traditional search. It's all Hombres de Paco, which was Spanish daytime television that somebody had just flooded the system with these things. And here's the recommendation search. It's Concierto Ciudad, classical guitar, Ciudi, which is a flamenco dance group, and then Vicento Amigo playing another Spanish classical bit of music, Van Halen doing a little tiny classical guitar riff during a concert, and then somebody in the dorm room doing freestyle flamenco, meaning I can't remember the actual piece, but I can do something that sounds like it. So these are all excellent hits, and it went down about 40 videos and then just stopped. It didn't produce anything that was garbage, produced everything that was interesting that we could find in the test collection. And we even prototyped and tested just a little bit this alternative example where we put a little icon on the website that had nothing behind it. It linked to another page, but that page was populated by recommendations for the people who click on that link. So people who click on the link are the ones who want to see the videos behind the link, which we don't know what they are. But after 20 people had done this, we knew that we would show what those 20 people want. So the 21st person would see what the 20 people before them would like to see, and it made people happy. Even though we had no idea necessarily what should be behind the video, behind the link, this gave us a self-organizing website that matched people's expectations. It was hilarious. Just 5 minutes after you put up a thing that says fast cars, all of the teenage boys who had clicked on that had taught it that you want to see girls in bikinis and fast cars behind it. And it made them quite happy. So this is a great example of how you can do cross-recommendation, get nice things. But what we want to do here is full-on multimodal. Multiple kinds of input, not just from one behavior to the same behavior, not just from one behavior to another kind of behavior. We want to go beyond that. So we want to do better. We want to start with this single kind of history that we had users and things, and we want to combine it into an adjoined matrix of users and things of type 1, users and things of type 2. Now, instead of doing A and B, we're going to put this all in the same matrix. Later, we'll be able to pull it apart for computational convenience. And we might even have the same type of things, or not, or just have different types of actions. Whatever sort of distinction we want to draw there is fine. Now, if we just elaborate the same thing that we did before with the A transpose A idea, except now with this generalized idea of multiple kinds of behavior, it follows through with just a little bit of math down to this lower form here that we can have behavior history H1 of type 1, H2 of type 2, and we have 2 recommendation matrices inside here in order to get recommendations for type 1. Now, we could recommend for type 1 and 2, but the idea here is that things of type 1 are what we want to recommend for, and things of type 2 are the other behavior we observe. So we're going to just keep the R1. And inside there, we have a conventional recommendation matrix, A transpose A, where A is A1. And then we have a cross recommendation, A1 transpose A2, embedded in the same system. So it's nice that the previous forms reappear. And so the summary here is that we just multiply multiple kinds of behavior into the same thing, and the weighting lets these integrate cleanly. And so the input is multiple kinds of behavior, the output is recommendations for one kind of behavior with different kinds of history. And cross-recommendation is a special case there. Now, we can do this again without the scary math part, without the big matrices. Suppose we have user transactions, say credit card transactions. These are user ID and the merchant ID, the industry code, the amount, possible descriptions of the merchant, maybe it's cuisine if it's a restaurant, and so on. We might have offers. So if I have one of these things, I might get special coupons that I would get as offers, and if I just move the coupons into my little coupon wallet, then I've got a second kind of action. And there I have the user ID and the offer ID and various metadata about the offer itself. And from these I can derive extra information about the user, extra information about the merchants, but more importantly I can do cross-recommendation between merchant transactions and offers and back and forth. And so I just find different kind of indicators, the anomalous indicators of each kind. And so in the search engine goes all of the information about a particular merchant or a particular offer, plus indicators. So if we're doing recommendations for restaurants, we might have indicators of text. That's the next to last one there. The text would be key words in the history of restaurant describing words with transactions I've done in the past. So a Chinese restaurant, for instance, might have as an indicator word Sichuan. If I have done transactions that have Sichuan in the word, in the description of those merchants, then that might cause me to be recommended Chinese restaurants. Indicator offers. If I've previously redeemed offers similar to the one here, those might become indicators. Industries. If I do a lot of business with airlines, airlines might have indicators there in these. And in particular, if I want to do geographical recommendations, I might just say people who are in this region should be recommended this particular offer. And so the query then becomes, that's the H on the right side, what's the current location of the user, and the recent merchant descriptions, and the recent merchant IDs, the recent SIC codes, the recent accepted offers, and of course, a 1, say, always give me local best restaurants. So you can see how to build this. This is not hard at this point, is it? You have 2 co-occurrence, 1 co-occurrence, 1 cross-occurrence analysis. That builds your indicators. You throw those into a search engine, and you provide these composite synthetic queries. It's actually very easy to build. You can use co-occurrence jobs from Mahout. They can run sequentially. They can run on a MapReduce setting. Of course, with my Red Hat, I like to run them on MapR. You drive those directly into a MapReduce that does Solr indexing, and then you deploy it with a web tier that does Solr search. The Solr can access shards that you pull out or directly on the cluster. And the Solr engine directly does all of the weighting needed to combine this data together. And shouldn't go on a slide and logo and things like that, but a customer of ours has actually built this cross-recommendation engine for restaurants. It's available on mobile phones. It's called My Offers. And an interesting historical aspect is they started with a pre-scoring sort of approach that a lot of people like, It took 20 hours per day for a very limited subset of users. It took 8 hours to move all those pre-scored recommendations to a database that they already had attached to their website. When they moved to the co-occurrence, cross-occurrence style, processing on 10 times as much data went down to under 3 hours, and the export time to Solr dropped to under 3 minutes. The recommendation generation actually took much less time and was more accurate. They also, in parallel, were trying to build a much more advanced decomposition-based recommendation engine. They fielded that in a test setting, and it was unable to compete because it could not integrate different kinds of information nearly as easily as this very simple system. And so it's not unusual to find that these simple systems built this way are more effective than more complex systems. So as promised, places to ping me, hashtags. By the way, we're hiring. And so I've arranged to have extra time here. We have 10 plus minutes. It's your turn. Do we have any questions? Would anybody like to make comments? Does anybody here want to build a recommendation engine?
I mean, yeah. So
okay.
Thanks, Ted, for your talk.
Thank you.